All right, welcome back. So today we'll be looking into electric circuits. First, we'll be talking about electrical elements. To start with, we'll look at capacitors. Okay. So the simplest capacitor would be like you have two parallel plates and facing each other, and you can charge them. So positive charge on one plate, negative charge on the other plate. So the capacitor can have different forms, like you have the simplest one, or you can have like two sheets of material separated by insulator in orange here in the figure here B, and you can roll into a cylinder. So a lot of times you see cylindrical capacitor, they are actually two sheets rolled into a cylinder, okay, in that sense. So the capacitor has the capacity to store both electric charge and also energy. So that's the name of the capacitor implies. The capacitance of capacitor is simply the charge that you have on the two plates and divide by the potential difference between the two plates. So Q over V, that's the capacitance. Its SI unit is coulomb over volts, or its own name is called Farad, symbol F for that. Okay. And these are some other types of capacity you might have, like cylinder ones will be pretty typical, this one and that one. And then you have like some circular ones, so the two plates inside it and separated by insulator, or like a kind of rectangular shape, but there's like, again, two sheets roll into or fold into that shape, okay? Some symbols in the circuit, so normally you get this one, all right? So then this is a common capacitor. If you get this one, that means it's an electrolytic capacitor. And then this guy, that means a variable capacitor. Okay. So for the parallel plate capacitor, so the way to calculate the capacitance is you start with the calculating what will be the electric field in between the plates. And then you also use that to calculate what's the voltage across the two plates, given this Q, okay? So if you have Q on the plate, and the density will be sigma equal to Q over the area of that electric field in between the two plates, we know that for one plate is sigma over 2 epsilon naught. Now you have two plates, one positive, one negative, so the electric field intensified by 2. So then sigma over epsilon naught. The voltage across the plate then will be distance times the electric field, E times D. So E is this guy, and then sigma D over epsilon naught. And sigma is Q over A, okay? So then you do Q over V according to the capacitance definition, then Q over this whole thing together. So Q and Q cancels, epsilon naught A comes on top, and then D remains at the bottom. So epsilon naught A divided by D then will be the capacitance of the parallel plate capacitor, okay? So again, you start with Q, and then you kind of work through to get V. So then Q over V will be your capacitance. So let's take a look at one simple example here. Says the place of an empty plate capacitor of capacitance 5.0 picofarad are 2.0 millimeter apart. What's the area of each plate? Okay, so it gives you C, it gives you D, asking you to solve for A. So for a parallel plate capacitor, we know its capacitance is what we had in the previous slide, which is C equal to epsilon naught A over D, right? So you're looking for A here. So A then equals to CD over epsilon naught. Okay, so you plug in your numbers. C is 5 pico minus 12 farad. Distance millimeter minus 3 meters over 8.85 times 10 to the minus 12 farad over meters. So that gives you 1.10 times 10 to the minus 3 meters square. Okay, so that's the area. So a simple application of capacitor for parallel plate capacitor. Let's go back to the slide. Okay. So to calculate different types of capacitor, in this case, you have like this is two pieces of metal shell. So the first one and the second one. So first one for the smaller one, inner one is positive charge, and the outer one is negative charge. So let's say if you have positive Q here and negative Q outside, right? So you can use Gauss's law to find what will be the electric field in between the two shell. Okay, so E times A in that case equal to Gauss's law says Q over epsilon naught. So then E equals to you divide both sides from here, divide both sides by 4 pi r squared. So 1 over 4 pi epsilon naught Q over r squared, okay, in the radial direction. The potential difference across these two shell, then integration from R1 to R2E dot dl, okay? So E is in the radial direction, so dl will be also in the component in the radial direction. That would be what you are taking. So then integration of this guy gives you, so constant numbers goes in front of integral. So 1 over r squared, right? So minus 1 over r then. So then it will be 1 over r1 minus 1 over r2 times this guy. Okay, so this will be v. So then q divided by v, okay, gives you this result as the capacitors of this guy. So again, given q, you are going to assuming q, what's the q there, and then use that q, you're going to find v and use the definition of c equal to q divided by v for that, okay, for the capacitance. A cylindrical capacitor like this, the central rod layer, positive charge, the outer negative charged. So then E field, again, you can use Gauss's law, you construct Gaussian surface with a cylindrical shape in between the two. And in that case, so E field, integration of E field in the normal direction, okay, so on the bottom side will be 0, and then only on this side we'll have the flux. So E times 2 pi r over L, and that should be equal to the Q enclosed divided by epsilon naught. Okay, so then you get this guy as the electric field, again, calculating the voltage between the two metal pieces. Okay, integration, now 1 over r to be integrated. Okay, so that gives you natural logarithm. Okay, so at the end you get the voltage, and Q over voltage will be your capacitance. Okay, so you guys can pause here and then check through the algebra on that, or the calculation on that. Okay. All right. So next, let's take a look on combination of capacitors. So there are two types of combinations, two types of simple combinations, let's put it in that way. So in parallel and in series, okay? And then for complicated complication, you may have some part of the circuit in parallel, and then with that part, with another part in parallel or in series, etc. But we are starting with the simplest cases for in series purely and then in parallel purely, okay? So if you have capacitor in series, so in series, that means they share the same charge, okay, for capacitors. And for resistors, then that means they share the same current, but basically current is charge over time t. So again, you can also say they share the same charge in a given period for instead of sharing current, okay, so either way. So when they're in series, they share the same charge. So then for this guy, if you have them three capacitors in series, they are original neutral, so zero charge on the plates. And then once you have them connected, so then this side will be positive charge, right? And because for capacitor, one side is positive Q, the other side should be negative Q. Now this wire is initially neutral, so then if you have negative Q here, so this will be positive Q. And then this guy will be negative Q. Again, due to net charge equal to 0, this guy will be positive Q, and then this will be negative Q. Okay, so that's what you should have. Well, the combination of these three can be treated as one single one. We call it the equivalent capacitor for the combination of these three in series. Okay. So then let's take a look at the algebra here. Let me show you on the paper. So if you have three of them, battery, and then this guy and this guy connected the second capacitor and then a third one. So positive Q minus Q, positive Q and minus Q, positive Q and minus Q. Okay, and you have C1, C2, and C3. All right. So then the voltage across this guy, V1, and then across this guy, V2, and then across this guy, V3, right, should add up to be equal to the voltage of the battery, which says it's called epsilon, but I'm going to just use V, so which is epsilon. Okay, so C equal to Q over V. So then V should be equal to Q over C, okay? So for V1 plus V2 plus V3, which equals to V, that means V1 is Q, the same Q over C1 plus V2 is then Q over C2 plus V for 3 will be the same Q over C3. That equals to the total voltage divided by the epsilon naught, which that's for the equivalent, right? So if this you have just one single equivalent CEQ, so then the voltage across this should be V, the same as epsilon, okay? So that would be then the Q over CEQ, okay? Because charges will be positive Q and then the other one will be negative Q in that sense. So the Q will be the same overall. So then you have 1, 1, 1, and 1. So 1 over CEQ equal to 1 over C1 plus 1 over C2 plus 1 over C3. Okay, just as the slide shows in the slide. Okay, so for 3 capacitors, you add them up, the inverse of them up to be equal to inverse of the CEQ. So then to calculate CEQ, you do summation of this, right? All these together and then do inverse of it. Okay, so that's when you have capacitors are in series. So you do inverse of each one, add them up, and then take an inverse of that for the equivalent capacitance of the combination. Okay, now when they are in parallel, so when you are in parallel, they share the same voltage because if you apply voltage across A and B, then that should give you the same voltage across C1, across C2, and across C3. Okay, so then at the end, you get the equivalent to be C1 plus C2 plus C3. Okay, and let me show you why that's the case. So, so these capacitors, they share the same voltage. Number 1, number 2, and number 3. Okay. So V are the same, and then this could be an equivalent of just 1, right? So just one CEQ in that sense. So V across CEQ, and this is V across C1, C2, C3. Okay. So for this guy will be Q total, right? Q total of like all the charges, right? On one side and on the other side add up, divided by V. Okay. And Q total is equal to Q1 plus Q2 plus Q3, which is C1V, right, plus C2V plus C3V. So then CEQ being Q total over V, okay? So then Q total can be CEQ times V equal to Q total. So Q total is this, Q total is also that. So CEQ times V then equal to C1V plus C2V plus C3V, okay? So VV will cancel across. So then you have that relationship of equivalent capacitance will be just equal to the capacitance of the each individual ones add up, okay, for if they are in parallel with each other, okay, so as the slide shows. So let's go back to the slide. All right. Now, sometimes you have a combination of capacitors in series and also as they are in parallel with another part. So in this case, not just simply in series or in parallel. So these two are in series first, and then the combination of these two is in parallel with this guy, okay? So we'll treat the part of a circuit that is having just purely in series or in parallel first, and then apply the rules for capacitors in series or parallel. And then use that as equivalent and then to combine with the another part, etc. Okay, so that means on this one we'll actually this is what we are going to do. We are going to treat the first one as the two at the bottom here in series first. Okay, so 15 microfarad, 8.2 and 22 microfarad. So we are going to treat this guy as an equivalent capacitor, right? So then when they are in parallel, right, you are in series. So CEQ of this guy will be 1 over 8.2 plus 1 over 22, right? And then inverse. Okay, so that gives you 5.97 microfarad. So then your circuit now is equivalent to, you just have this 5.97 microfarad one that is in parallel with the top one of 15 microfarad. Okay, so then when they are in parallel, you actually just add up. Okay, so let me call this as prime, and then so the final one will be CEQ of these two in parallel. You add them up. Okay, so that's about 21 microfarad for the whole circuit. Okay, so that's how you're gonna do. If you have more complicated ones, then treat the path is either in series or in parallel first, and then move on from there on if to see if that part is in series or in parallel with another part. Okay, and then etc. Just moving on one by one. All right. Another example, but in this case, you are connecting and disconnecting a capacitor. Okay, so in this case, it says 100 and a 400 picofarad capacitors both charged to 2.00 kilovolts. They are then disconnected from the voltage source and are connected again, positive and negative plate, and negative to positive and positive to negative. Okay, so find the resulting potential across. Let's sketch the problem and then try to understand the problem first. Okay, so it says, so initially you have them charged. This guy, both of them both charged to the same voltage. So that means they are in parallel. Okay, parallel, and then they are charged to across this as 2 kilovolts. Okay, so 2 kilovolts across the two terminals here. And this guy is 100 micro pico, and this guy is the 200 or 400 pico. So let's call this positive, this negative. So then we know that we'll have actually positive charge deposit right on the top plate here, and then negative on the bottom, and then the same here, positive and negative on the two plates. So this is what happens initially. And we can calculate, right, what will be the Q here. So let's call this positive Q1, negative Q1 here, and then positive Q2 and negative Q2. So Q1 then will be equal to C1 times V, the same V. So C is 100 pico farad, 2 kilovolts. So that's 200 times 10 to the 9, so that's positive 3 minus 9 coulombs. Okay, and for Q2 would be C2 times V, so that's 400 minus 12, 2.0 times 10 to the third. Okay, and that gives you 800 times 10 to the minus 9. Okay, so that's what happens initially. Now you disconnect the two, disconnect, and you connect so that the positive is connect to the negative, and then the negative is connect to the positive. So in that way, okay. So what happens now? Let's flip this guy, or this guy, doesn't matter. Okay. So what happens now is you have, let me say I flip the first one, so minus minus and positive positive. Okay, and connect it to positive, positive, negative, negative. Okay. So then it's asking you, what's the resulting potential across each plate? Okay. So let's analyze this, what will be happening, right? So you have minus Q1 here, positive Q2 on top, positive Q1 at the bottom, minus Q2 at the bottom, right? So when you connect the two plates, so there will be charge redistribution, right? Negative and positive will cancel and partially because Q1 and Q2 are not the same amount. And then the same thing here for positive Q2 and minus Q2, right? So on the top plate, the top plates, there'll be exchange of charges and then the negative plate as well. So let's see now what happens. So there should be equilibrium status reached at some point later, right? So then these two top plates are connected, these bottom two plates are connected, right? So then this becomes a for on the top plate, because they are connected, so they will have the same voltage, right? And then the bottom plate, they are connected, so they will also have the same voltage. So it looks like the voltage across the two should be equal to each other. So that means, okay, again, they are in parallel to each other, okay? We can put it in that way. So if they're in parallel, then we can calculate, we can treat this one as an equivalent, right? Just an equivalent CEQ of the two in parallel, right? So CEQ of into two in parallel should be just C1 plus C2. So that would be 500 picofarad, okay? Now we are looking for the voltage across. So that means if we can calculate what will be the total charge now on the top plate and then on the bottom plate. So then we should be able to just use CEQ equal to Q total divided by V, right? Or divided by the V, that's what we are looking for. Okay, the voltage, you are looking for that voltage. So then V is equal to Q total over CEQ, okay? So let's look at what's Q total. Q total is equal to positive Q2 minus Q1, right, on the top place. So positive of 800 minus 200. So that gives you 600 times 10 to the minus 9 coulombs, okay? So then V equals to 600 times 10 to the minus 9 coulombs over 500 pico farad. So that's 1.20 kilovolts. Okay, that's on that one. So at the end, you'll get about 1.20 kilovolts for the new combination. Okay. All right. So back to the slide. So we have talked about the charge on the capacitor, right? So now let's take a look on the energy stored in the capacitor. Okay. So if you have charge positive Q build up between the two plates, then how much energy is stored there? Okay. So so how much energy stored, you can think about like basically charging a capacitor means that you take positive charge from the negative plate and then place into the other plate, right? So for example, you remove one coulomb to the other one, so then the other one will be 1 coulomb positive, the other one will be negative 1 coulomb charge, right? So then the during the process, there will be electric field build up, then there will be like potential difference across like V, okay? So V, according to C equal to Q over V, so then V is equal to Q over C. Okay, so then when you are doing this, by doing this, you are actually doing work against the electric field. So then there will be electric potential energy build up. Okay, so equal to V times dQ and Q over C dQ. So then integrate through this side gives you U, on this side gives you then this expression, which gives you Q square over 2 divided by 2C. Okay, so that's the energy. Or you can think about it in this way. So the V over versus Q chart, right? So the area underneath the curve will be the energy build up. So then that gives you 1/2 of the Q over C times Q, the same as this guy. Now this expression can be rewritten as 1/2 Q times V or 1/2 CV squared, because C equal to Q divided by V, okay? So either of those expressions should be just fine. So let's take a look on the electric field energy stored there. So energy stored in the capacitor is 1/2 QV. Okay, and Q V is E times D. Okay, so V is equal to that. Q is equal to epsilon naught times E times A. All right. So in that sense, so this is because E is equal to sigma over 2 epsilon naught. Okay. So then Q is equal to sigma times A, or actually E is equal to sigma over just epsilon naught, okay, because this is parallel plate, you have two plates. So then this gives you the area's charge density. Sigma times E will be, or epsilon naught times E will be equal to sigma. Sigma times A will be Q, okay? So then your energy is also can be written as 1/2 epsilon naught E squared times A times D. A is the area, D is the separation of the capacitor. Now A times D can gives you a volume, okay? So then this is volume, this is at 1/2 epsilon naught times E times volume. So then if you do divide by the total energy by volume, then it gives you this guy, okay? So the energy, total energy divided by volume, that would be the energy density. Let's use lowercase u sub e, that means energy density for electric field. S equal to 1/2 epsilon naught times E squared, okay? And this is without the dielectric. And later on, we'll see if you have dielectric, actually this will be intensified, okay, by the dielectric constant, okay? All right, but let's take a look on this example first, okay? This one says you have a capacitor, 225 microfarad, okay? The potential difference between the two plates, 345, and the separation is 0.223 millimeter. What's the electric energy density, okay? So to calculate electric energy density, we'll use then 1/2 epsilon naught E squared, right? So that's what we're going to use. So let's take a look on how to solve for this one. So we are looking for the energy density, small u sub E equal to 1/2 epsilon naught electric field square. So the only goal here looks like is to find the electric field, right? Because this is a constant. Now it tells us C equal to 225 microfarad. It tells us delta V, or the V between is 345 volts. And it tells you D is equal to 0.223 times 10 to the minus 3 for millimeter. So I think we can just use these two because E is equal to delta V over D. Okay, so then we can calculate this. So energy density will be 1/2 epsilon naught times delta V over D to the square. So 1/2 8.85 10 to the minus 12 farad over meter times 345 volts divided by 0.223 10 to the minus 3 meters at the bottom, and squared it. So this gives you 10.6 joules to the meters cube, okay, on the density, energy density stored in the capacitor. All right, so next section here talks about the dielectric constant, okay? So when you have dielectric in between the two plates of parallel plate capacitor, its capacitance actually increases. Okay, so what happens here is initially you just have vacuum, so you have uniform electric field. Now you have dielectric inserted, right? So now the molecules in the insulator, which is called dielectric, will reorientate due to the electric field. Okay, so there's a dipole there and then reorientate. So as the electric field lines end at the negative charge, okay, start at positive charge. So you can see as the molecules are reoriented, so then there's charge cancellations in the region between the two. So you will expect less electric field lines than the previous one. So that means E field is being reduced. If E field is reduced, then voltage across the two plates will be reduced, right? Now C equal to Q over V. Q is the same, but V being reduced. So C will be increased. Okay, so that's how the dielectric actually increase the capacitance of capacitor. And that's increased by a factor of called dielectric constant kappa, not K, but the amount of electric field being reduced is equal to the initial electric field divided by kappa. Okay, so then C as a result will be kappa times the original capacitance. Okay, so dielectric constant for each material is an intrinsic property. So if you know the material, you know the dielectric constant, or the other way around. You can find the dielectric constant, you can look it up and identify the materials. Okay. So some common dielectric constant for materials are listed here. Water is 80.4, mica 40.4, air about 1, vacuum is about 1. Okay, so epsilon naught is the permittivity of vacuum. So then permittivity for the material should be just kappa times the epsilon naught in that sense. Okay. So without dielectric, we know capacitance is equal to epsilon naught times A over D, but with dielectric, then that is increased by kappa, or just the permittivity of the material times A divided by D, okay? So energy stored then as a result will be increased because C is increased by kappa. So energy stored should be increased by kappa. So it will be equal to 1/2 kappa epsilon naught E square, or just 1/2 epsilon permittivity for the material times E squared. Okay. Let's take a look on one example here. So it says a parallel plate capacitor. It's made of 2 aluminum foil sheet and has the length and width given. Between the sheets is a Teflon strip of same width and length, that is the thickness of 0.025 millimeter thick. Was the capacitance of the capacitor. Okay, so now we will be calculating capacitance with the dielectric. Okay, so for parallel plate capacitor, capacitance is without the dielectric is that guy, right? But with dielectric, you multiply by kappa. Okay, so 2.1 kappa is the ratio of the permittivity of material to vacuum, so no units, and 8.85 10 to the minus 12 farad over meters. The area should be the width by length, right? Width by length 10 to the minus 2 meters divided by the thickness 0.025 times 10 to the minus 3 meters. Okay, so that gives you 1.7 times 10 to the minus 12 farad, okay, or picofarad. All right. Let's go back to a slide. All right. So insulators are not always insulating. If you apply very large voltage across it, then you might be able to break it down, make it conductive. So for different materials, the strength of the field needed is different. So mica is 100 million volts per meter. Air is 3 million volts per meter. Okay, so just keep that in mind. This is called dielectric breakdown. All right, I think we will stop here and then we'll come back for the remaining sections on this topic. Okay, I'll see you guys later.